All right, folks, this chapter is all about igneous rocks, chapter 4, right? But before we talk about that, let's talk about kind of rocks in general. There are generally are three major categories of rocks here. We have igneous rocks, which we'll be talking about today, root of that word, ignite, fire, right? Flame. These are rocks that form from, a liquid, so a lava or a magma, right? Then we have sedimentary rocks, root of that word, sediment, to settle, right? These are rocks that are laid down in fluid, either air or water. And then we have metamorphic rocks, and these are rocks that have changed, right? Root of that word, metamorphosis. These are rocks that have changed in the their physical and chemical components, but in the solid state, they've not become liquid, right? That would make them an igneous rock, but they change in the solid state, right? I was taking a look here. We have the rock cycle, right? We got cycles for everything. We start with igneous rocks that go from magma or lava, right? Those get weathered, eroded, transported, deposited, make sedimentary rocks, right? And then those get squished and buried, and it becomes metamorphic rocks. Of course, those then remelt and become igneous rocks, or we can weather metamorphic rocks into sedimentary rocks, or metamorphose igneous rocks, or weather however, right? So we can go back and forth in all sorts of different paths in the rock cycle, right? To make sure that was working. It didn't work last time. Anyway, so looking at igneous rocks, right? First of all, we have magma, right? Magma is formed under the earth for a variety of reasons. We'll look at that later in this chapter. It cools and it solidifies, right? Partial melting of the mantle or the crust forms magma, which is a liquid, right? Now it's liquid. That's going to be less dense. It's going to rise buoyantly, right? Sometimes it pokes through the crust and becomes, lava eruption at a volcano, or sometimes it cools over millions of years under the ground and becomes, a plutonic or intrusive igneous rock, right? We have two types: extrusive or volcanic, extrude, right? It's shot up onto the earth, right? So that's volcanic rocks. Those are rocks that are made from lava. Lava is on the surface. And then we have intrusive igneous rocks or plutonic igneous rocks. These are rocks that cool deep into the ground, right? So that liquid magma has risen buoyantly and intruded into this area and cools, deep in the earth to form intrusive igneous rocks, right? So forming these rocks, first we have, the source of that partial melting for whatever reason. We'll talk about that later this chapter. This, now becomes less dense since the liquid that starts to rise. It can, gather at various depths in these big magma chambers. And then it can, from time to time be, shot up onto the face of our Earth as an extrusive igneous rock or volcanic igneous rock formed from lava. Again, so lava is, basically from, somewhere kind of right in the volcanic neck out, right? Anywhere it's in contact with kind of a surface environment. And then the underground stuff, this is all magma, right? Same stuff, liquid rock, but, on the surface it's called lava, in the ground it's called magma, and that alludes to our two different types of igneous rocks, right? Extrusive and intrusive. What's in magma? Well, surprise, surprise, silicon, oxygen, aluminum, potassium, sodium, calcium, iron, magnesium. They're back to haunt us again, right? Here are some pictures of them, the 8 most common elements on our planet. There are gases dissolved into the magma. Deep under Earth, there's enough pressure. They don't exist as bubbles. They're just dissolved into the magma, right? And then we have temperatures that, from about 700 degrees centigrade to well over 1,000 degrees centigrade, right? Olivine, our highest temperature minerals, start to crystallize out at some of those highest temperatures, 1,200 degrees centigrade or so, right? The process of crystallization, right, through in these magma chambers, we looked at that kind of last time, but let's go through it a little more closely this time, right? So at the highest temperatures, right, there are no crystals, there are no solid form, right? It's all liquid. All these atoms and ions are disordered, moving around quickly. But as we start to cool things down, now they can start to stick together, right? Start to have parties, make crystals, right? And then now we have, say, an olivine or something, right? As it cools down even more, we get more and more complex silicate structures, right? So again, at those lower temperatures, right, we're going slower. We can start to form those more complex silicate structures from the silicate tetrahedrons, right? And we start to form a variety of minerals, right? If this occurs slowly over millions of years underground as an intrusive igneous rock, right, all of this liquid will have time to get together and make minerals, right? If it doesn't, right, whatever gets shot out to the volcano, whatever was happily forming minerals will be in there, whatever was liquid will be in there, and gas will be in there, all of that, right? So let's take a look at this process of crystallization a little closer here. Now this is a good description of crystallization, right? This one is actually showing it with acetaminophen. So this is a medicine, but the same process, right? We're going to pretend this is our magma chamber. Here's all of our elements and ions, right, in our magma in the liquid, right? As we first melt that rock into an igneous, right, into a magma, right? At the highest of these temperatures, everything's going to be liquid. Look at that, everything dissolves, right? No crystalline structure at all, no solid at all. But now, as we start to cool things down, check it out, right? We start to form what we call embryo crystals or a seed crystal, right? Now it's a blueprint basically for the other elements and ions to know, okay, this is where I'm supposed to go, right? They all get together, they have element and ion parties, and they make crystals, right? So say this is our simplest one, maybe like an olivine, right? A nice little crystal, right? Well, in this case, acetaminophen, but you get the idea, right? That process of crystallization happens very similarly in a magma chamber, right? So as this process of crystallization occurs, first of all, right, the silicon oxygen bonds start to form. We talked about this in the last chapter, right? We just get those tetrahedra, right? At the very highest temperatures, those isolated tetrahedra join with, iron and magnesium and start to form, those olivine crystals, right? Those solid, isolated tetrahedra, right? So looking from, say, this frame here, first frame 1, to frame 4, let's pretend for a minute this is a closed system. Nothing is coming in or going out. We have the same amount of each element and ion from the start to the finish. But what we're looking at here is the difference between the liquid phase and the solid phase, right? So as we pull out these, say, olivine crystals, we're pulling out a lot of iron, we're pulling out a lot of magnesium, and we're pulling out a lot of oxygen, right? 4 oxygen for every 1 silica. We're not pulling out as much silica, a lot of iron, a lot of magnesium, a lot of oxygen, right? So as we do that, right, we start to deplete the rest of the liquid from those materials that we've removed, right? Iron, magnesium, and oxygen, right? We cool things down a little bit more, right? And those more crystalline embryos start to form, right? Those seed crystals. This time, let's say it's our single chain silicates, those pyroxenes, right? Now we're pulling out, iron and magnesium still, and 1 silica, but now only 3 oxygen for every 1 silica, but still lots of iron, lots of magnesium, quite a bit of oxygen, right? Leaving the liquid, right, yet further depleted in that iron, right, and oxygen, right? So on more, other these join crystals, now we have, let's say, we got these double chains forming here, right? And as this forms, right, now we're pulling out, iron, magnesium, right? Not as much oxygen per silica. I think it's 22 to 10 or something like that, or 22 to 11. I don't know. Anyway, something like that. But so anyway, but we're pulling out still quite a bit of oxygen, iron, and magnesium, right? So by the time we get to here, we have a liquid that is very depleted in iron and magnesium and oxygen, right, relative to how it started, but very enriched in silica, right, making this our ferromagnesian, right, and this one non-ferromagnesian, this one mafic, this one felsic, right? This is how we can evolve from a mafic or ferromagnesian lava to a felsic or non-ferromagnesian lava, right? Anyway, so as these crystals form, right, and this magma changes, right, a couple other things happen as well, and they have to do with density, right? Density back to haunt us again. So we're forming those iron and magnesium rich, those denser, those mafic, those ferromagnesian minerals, right? And you know, compared to the relative density of the magma now, those are denser, so they're going to sink, right? And at the same time, you know, the felsic minerals that form, right, the ones that are going to have less iron and magnesium in their structure, those are going to be, you know, relatively less dense than the residual magma, and they're going to rise, right? So you get these separation or crystal settling, right? Fractional crystallization is what it's called, right? So we can see here a lot more light color up at top, a lot more dark color up at bottom. This is doing to that settling effect, right? My son loves Minecraft, so here we go, right? But what is magma made up of? It's the liquid component or the melt, right? This is, right, all the elements and ions still in the liquid form. Solid components of crystals had formed, right? Whatever silica crystals, those are going to be our solids. And then our gases, right? Also known as volatiles, water, carbon dioxide, sulfur dioxide, fluorine gas, this kind of stuff, right? But in a magma chamber, again, under pressure, not going to exist as bubbles, right? They're going to be dissolved into the magma. So magma is the melt plus whatever crystals have formed plus the gases that are involved, right? That's what's in the magma just sitting in the earth, right? Now, when we take that magma and we throw it up onto the surface and we turn it into lava, which then cools into an extrusive or volcanic igneous rock, we see these same three phases, right? What used to be liquid, or you know, was liquid in the magma when it got spit out as lava, right? That is now what we call ground mass or matrix. This kind of this dull, right, boring-looking stuff, right? That's just volcanic glass. It's just frozen elements in space and time, essentially, right? We then have crystals or phenocrysts, right? These are the formerly solid component, whatever was growing and forming in that magma chamber before it erupted, right? So here we have some plagioclase phenocrysts or crystals that were happily chilling and forming when this volcano erupted, right? And then we have gas bubbles or vesicles, and these can represent the formerly gas component. Now that it's come up further, you know, into the volcanic neck, less pressure allows these bubbles to nucleate, right? And then sometimes you see those escape, right? So volcanic igneous rocks, we have matrix always. Sometimes we have crystals, sometimes we have bubbles, sometimes not, right? So volcanic rock, matrix, plus or minus crystals, plus or minus bubbles or vesicles, right? Magma cooled at depth, however, is called plutonic igneous rock or intrusive igneous rock, right? This is made of entirely crystals, solid crystals. In these case, we have, you know, millions of years for these magmas to cool, right? All of the elements and ions have time to get together and have parties and make crystals. Everything turned solid into crystal form, right? So plutonic igneous rocks, entirely crystal, right? All right, folks, we'll see you next.